Alright guys, this is lesson 2-8. Sorry, did not put that here. 2-8. Linear inequalities and systems of inequalities. Our objective today is that we're going to graph linear inequalities, we're going to write linear inequalities to represent real-world situations, and we're going to solve systems of inequalities. And so really the biggest difference between an inequality, a linear inequality, and a linear equation is really just that inequality symbol. And so the first part of our notes is we're just going to define linear inequality. So in our Q, linear inequality, and we're just going to define this. A linear inequality is similar to a linear equation, however, with an inequality symbol instead. So pretty simple explanation there. And so the way that we graph these, we follow the exact same steps as graphing a linear equation. We just have a couple other rules to follow. And so if we take a look at a linear inequality, we might have something like this. Given y is greater than or equal to negative 2x plus 9, which points satisfy the inequality? And what that means is that word satisfy, that just means which points would make our inequality true. Which points make the inequality true? Points that make it true. That's what satisfy means. So let's say I'm given some points here. Let's say I'm given, we'll call this the first one, point A, 7, 4, and then I'm also given another point, negative 1, 3. If it's asking which points satisfy the inequality, that just means I'm going to evaluate this inequality given, y is greater than or equal to negative 2x plus 9. I'm going to evaluate it for x is 7 and y is 4. And so all we do here is we're just going to plug these values into our inequality. 7 representing x and 4 representing y. So using this inequality here, that would give us 4 is greater than or equal to negative 2 times 7 plus 9. So once we simplify, if we end up with a true equation, then this point does satisfy our inequality. So we just need to simplify. Negative 2 times 7 is negative 14, plus 9 is negative 5. Is this a true equation, or is this a true, inequality rather? And yes, it is. 4 is greater than or equal to negative 5. So this point satisfies our inequality. Again, you just take your ordered pair and you substitute the values in for x and y in your inequality. I would like you to check this next one. Plug it into the inequality and then see if you get a true equation. So when I plug in these values, I get 3 is greater than or equal to negative 2 times negative 1 plus 9. And then I simplify. Negative 2 times negative 1 is positive 2, and positive 2 plus 9 is 11. 3 is not greater than or equal to 11. Therefore, this point does not satisfy our inequality. So, taking a look at a real-world example, and that's what we'll label our next Q, real-world example. I'm going to go ahead and write down the example and then I'll read it out loud together. Alright, so we have this example. John sells t-shirts. Plain shirts cost $5 and graphic shirts cost $7. In order to match his product costs, he must make at least $1,200. So let's say we have something that asks us, if John sells 150 plain shirts and 60 graphic shirts, will he be able to cover the product costs? In order to answer this problem, we need to write an inequality to represent the situation, and then substitute these values for plain shirts and graphic shirts into our inequality. And so first step is to write an inequality. Okay, so we know that plain shirts cost $5 and graphic shirts cost $7. And in order to match his product cost, he needs to make at least $1,200. All of that information is going to help us write our inequality. We're going to do the cost of the plain shirts plus the cost of the graphic shirts has to be at least, so greater than or equal to $1,200. We know that plain shirts are $5 each. So $5 times the number of plain shirts, I'll use P for plain, plus $7 times the number of graphic shirts, I'll use G for graphic, has to be at least, so greater than or equal to 1,200. This inequality represents our situation. Now we're given the example that he sold 150 plain and 60 graphic. Will he be able to cover our product costs? We just have to see, does this ordered pair, 150 for P and 60 for G, satisfy the inequality? And so step 2 is substitute 150 for P and 60 for G to see if it satisfies the inequality. So we've got 5 times the number of plain shirts, which is 150, plus 7 times the number of graphic shirts, which is 60, has to be greater than or equal to 1,200 in order for this to cover his product costs. Now we're just going to simplify. 5 times 150, and we get 750, plus 7 times 60 is 420. When we add those together, in order for this to be true, it has to be greater than or equal to 1,200. So when I add those together, we get 1,170 is greater than or equal to 1,200. This does not satisfy the inequality. And so our answer would be no. This would not give him enough money to cover his product costs. Next, we're going to take a look at graphing inequalities. So please prepare your graph paper, and when we're done with our graph paper, we're going to tape it into our notebook just like we've done in the past. Our cue for this will be graphing linear inequalities. We're going to write down some steps first, okay? So, step number 1. The first thing we want to do is rewrite the inequality in slope-intercept form. How do we do that? How do we write something in slope-intercept form? So in order to write something in slope-intercept form, we need to isolate y. When we do that, because this is an inequality, we have to remember the golden rule. So the golden rule still applies. What is the golden rule of inequalities? Anytime we multiply or divide by a negative, we have to flip the inequality symbol. Step 2. We're going to graph the line just like we would if this was a linear equation. Plot the y-intercept and then use our slope. Now, there are some things that we are going to add here. Because this is an inequality, use a dashed line for greater than or less than symbols. And a solid line for greater than or equal to or less than or equal to symbols. And then the third step, after we've graphed our line, we've used a dashed line for less than or greater than, we've used a solid line for greater than, equal to, or less than or equal to. The last step would be to shade. We're going to shade above the line, and so that's where y is going to be greater than. We want to shade above the line for any greater than symbols, so greater than or equal to, and below the line for less than or equal to symbols. Now the reason that we do that is because an inequality does not show us just ordered pairs on the line that satisfy the equation, rather a region of the graph that satisfies our equation. And so we're going to take a look at some examples here. The first one we're going to take a look at, so example 1, is 5x plus 3y is less than or equal to 12. And so following our steps, the first thing we want to do is rewrite the inequality in slope-intercept form. And so in order to do step 1, I'm just going to write it in the same color of my notes here so you can see the difference of the steps. So first we have to isolate y. We have 5x plus 3y is less than or equal to 12. We're going to isolate y by eliminating our x term from the left by subtracting 5x. Whatever we do to one side, we have to do to the other. Bring down the 3y, our less than or equal to stays the same. We didn't divide or multiply by a negative. And now to write this in slope-intercept form, I'm putting my x term in front, just like we've practiced. And then my positive 12 will go in the back. The last step then, to write this in slope-intercept form, we need to isolate y further by dividing by 3. I have to do that to every single term in my equation, or in my inequality. So I have y is less than or equal to negative 5 thirds x, that's my slope, plus 12 divided by 3 is 4. And so here is slope-intercept form of that inequality. Step 2, we want to graph the line. And so to the right here, I'm going to draw a coordinate plane. I see that my y-intercept is a positive 4, so I just want to keep that in consideration when I'm drawing this graph. And so I'm going to come all the way up here, and that should be good. Alright, so graph the line. I'm going to do this in green just so it matches my steps. Plot the y-intercept first. So the y-intercept is 4. So I'm going to go up 4. 1, 2, 3, 4, and I'm going to put a point. Then use the slope. We're going to use the slope to find more points in the line. So negative 5 thirds, that means my slope is going to go down to the right. So down 5, 1, 2, 3, 4, 5, to the right 3, 1, 2, 3, and put a point. And then I can do that again, down 5 more, 1, 2, 3, 4, 5, to the right 3, and put another point. Now it says, use dashed line for greater than or less than symbols, and a solid line for greater than equal to or less than or equal to symbols. Well, if I take a look here, this symbol has an equal to, and so I know this is going to be a solid line. And then our last step is going to be to shade. So let's draw that solid line. And now we need to shade. It says shade above the line for greater than or equal to, and below the line for less than or equal to. So looking at this symbol, I have less than or equal to, so I'm going to shade below. Below meaning where y is going to be less than. And so that's going to be all of this area right here gets shaded. That means that all of the ordered pairs in this region satisfy the inequality. All ordered pairs in this region satisfy the inequality. We're going to take a look at one more example. X minus 6y is less than negative 12. Okay, so step 1, write this in slope-intercept form. So that means we want to subtract x from both sides to eliminate the x term and isolate y, which leaves us with negative 6y is less than negative x minus 12. Remember that x term always goes in front of the y-intercept. Then, to isolate y further, we've got to divide by negative 6. And here's where our golden rule applies. Because we're dividing by a negative, our symbol has to flip. Y is now isolated. We have greater than, and then negative x divided by negative 6. Well, we could say this is negative 1x divided by negative 6, which is positive 1/6 x. Negative 12 divided by negative 6 is positive 2. And so now we have our equation in slope-intercept form. When we graph the line, we want to look at this inequality symbol here means it's a dashed line. It is not a solid line. That just means that any ordered pair on the line itself will not be included in our solution region. And then for our shading, this also means we're going to shade above the line this time because it's greater than. Above meaning where our y's are going to get greater than. So drawing this coordinate plane here, it looks like I've got a y-intercept at 2. We just want to give enough space to draw our lines here. Okay, y-intercept at 2. Our slope is positive 1/6, which means my line is going up to the right, up 1 to the right 6. Now I'm going to run out of space if I try to go up 1/6 again. So the corresponding direction from my y-intercept could be down to the left, down 1, left 6. 1, 2, 3, 4, 5, and 6. I can do that as long as my slope stays positive, which it is. If I was to connect these dots now with my dashed line, I'm going to have a positive slope. And then we need to shade above. Anything in this solution region here would satisfy my inequality. I could pick any ordered pair here or above here, and it would work in my linear inequality. Next, we're going to take a look at systems of linear inequalities. And so all that is just two inequalities graphed on the same number line. So I'm going to set up a fresh sheet of graph paper here. In our queue, we've got systems of linear inequalities. Now the difference between a system of linear inequalities and a system of equations. For a system of equations, the solution is an ordered pair where those two lines intersect and meet at that point. For linear inequalities in a system, your solutions are actually going to be a set of ordered pairs, a whole bunch of ordered pairs that would satisfy the system. And when we graph these, we're going to have two inequalities on the same number line with all of the shading that we've learned so far, and there's going to be a section of the graph where the shading of both inequalities will overlap, presenting a solution region. And so that's the difference. For a system of equations, it's one point. For a system of inequalities, it's all the solutions in that shading overlap. The solution to a system of linear inequalities is the set of ordered pairs that satisfy all the linear inequalities. step one would be to graph and shade each inequality in our system. So step one, graph and shade each linear inequality. And then step two is just to know that the solution to the system is where the shading overlaps. In order to graph each linear inequality, we want to follow the same steps as we just learned when we graphed single linear inequalities. We want to rewrite them in slope-intercept form, and then we'll graph them on the same number line. So here is an example. X minus y is greater than 1, and the other inequality is x plus 4y is greater than 20. Well, in order to graph these both, we've got to rewrite them in slope-intercept form. So what I'm going to do is, just in order to keep these organized, I'm going to label the first inequality in green as number 1, and the second inequality in blue as number 2. Labeling them helps keep my work clear and in order. And so I'm going to deal with first one and rewrite that in slope-intercept form. So inequality 1 is x minus y is greater than 1. In order to rewrite that in slope-intercept form, I want to isolate y. Subtract x from both sides. So I have negative y is greater than negative x plus 1. Now divide by negative 1 to get rid of that negative that's in front. Now remember, when we multiply or divide by a negative, our inequality symbol has to flip. And so I've got y is less than negative x divided by negative 1 is positive x, and positive 1 divided by negative 1 is negative 1. So here is the first inequality in slope-intercept form. Now I'm going to rewrite the second inequality in slope-intercept form as well. So we have x plus 4y is greater than 20. Isolate the y term by subtracting x from both sides. We have 4y is greater than negative x plus 20. Next, I'm going to divide by 4 each term. And so y is now isolated. Y is greater than negative x divided by negative 4. Well, we could put a 1 in front of here, right? And so that's the same as negative 1/4 x. So that's our slope. And then 20 divided by 4 is 5. All right, so we've got inequality 1 and inequality 2. We are ready to graph these on the same coordinate plane. All right, so I'm going to go ahead and draw myself a coordinate plane here. And what I'm going to do for these ones, you guys, is I'm going to make each unit, so each box, worth 2. And so I'm going to show my tick marks here. I'm going to put a tick mark in the middle of each of these boxes. So each box is actually worth 2 units. That's just going to give me a little bit more space to graph these inequalities. Okay, so here we go. So if I take a look at the first inequality, let's start with that one. My y-intercept is negative 1. So I'm going to put a point at negative 1, which is right here. My slope is, well, there's not a number in front here, but we could put a 1. And so my slope is 1. So I'm going to go up 1 over 1, up 1 over 1, and I'm going to keep plotting points until I run out of space on my coordinate plane. I'm going to go to the left of my y-intercept now and plot these points following the same slope, just this time it's down to the left. Now looking at this inequality symbol here, that means that this is going to be a dashed line. I have to remember that because now when I connect the dots, I'm using a dashed line, not a solid line. These ordered pairs on this line do not actually represent solutions. It's everything below the line. So we're going to shade below. So all of these ordered pairs in my shading here will represent solutions to this inequality. Now we're going to graph the second inequality. Looking at my y-intercept, it's at positive 5, so up 5. 1, 2, 3, 4, 5. And then my slope is negative 1/4, so down 1 to the right 4. 1, 2, 3, 4. Again, down 1 to the right 4. And we're going to keep following that pattern. Now that I've run out of space to the right, I'm going to use that same pattern but to the left. So that means up 1, left 4. Now looking at this symbol here, we have a dashed line here as well, so dashed line. And our shading this time is going to be above because it's greater than. So same thing, we've got a dashed line to connect these dots, but this time I'm going to shade above the line, including this part where we're overlapping. Because where the shading overlaps is actually our solution region. So if we take a look, our shading is overlapping over here. We have some green and some blue. I'm going to label this very clearly with an S for solution. This represents our solution region. So when you're doing your practice, that's what I want you to do, is to label it clearly with your S for solution. So this is our solution region. Any ordered pairs that are in this region of our graph that's shaded, this combined shading here, would represent solutions to our system.